So this one opens up at 1 today and closes Friday at 11 a.m. Yes.
It says Tuesday.
Yeah. Yeah. I'll change that to Friday.
Okay.
Okay. No, sorry about that. I'll change it to Friday. So it starts today at 1, ends on Friday. Right? So, again, pay attention to the way I'm asking for you to answer. If I say do a one word or use the acronym, please do so. So it's easier to grade.
Friday at 11 p.m. or
AM. Because then I wanna go over it before I meet with you all Friday. So I can hopefully dispel any misperceptions and get you back on track. Because we do have an exam, not this Friday, but the following Friday. So this is trying to get you going for that. And so it's similar in length to the last one. It won't take you really long. It's all open book, open note. So please remember to do this by Friday. I'll change that when I'm done with class today. So last time we met, which was a while ago, I wasn't even well enough to go to the UP 200. Did anyone go?
Yeah.
Oh, I'm glad good to hear a lot of you went. Pardon?
Fun and smell.
Smelly?
Oh, yeah.
The dog smelly
Oh,
or?
yeah. Dogs raised by,
They're
just
heated
going to the
up.
bathroom right as they're running by. You guys didn't get that? It was. It was like an entire team that went.
Zip it by.
Just flies
Just
out
let
the
it
back,
go.
like, whoa.
Wow.
The wave.
Well, that's impressive. Get video of that. Yeah.
Jumping up higher and I got the shoes stuck in the angle tonight. And like, all right.
Yeah, they get so excited. It's so fun to watch. I was unable to go because I wasn't feeling well, but I did have to run a short errand and I saw a ton of people walking toward, downtown. So I was like, good, there's gonna be a big crowd and good, yeah. All fun. I wish I could have gone. Well, I'm glad a lot of you went. That's a really special thing to experience. So, I think we left off around here. We were kind of going through the idea of roots can be specialized depending on their habitat. Here you're looking at the pretty impressive buttress roots because a lot of tropical soil systems don't have a lot of depth to the good soil, so to speak. So the depth that's really good for root access to minerals is pretty shallow. And because of that, their root systems just don't really go that deep. And so they have to compensate for that. So their trees won't topple over, the above ground portion. So putting this really strong architectural design of these buttress roots, an architect would definitely approve of this. If you're gonna have this tall shoot, with heavy branches and just to keep it more stable. And so they can get impressive. And so again, they're adapting to their current habitat, which is a fairly shallow soil system. And so they compensate with this. We also talked a little bit that they can do this action of kind of wetting and drying of their tissue causes this contractual movement. And this is trying to show this deeper and deeper pulling down essentially into the soil just through simple wetting and drying actions of the root tissue over time. And so you can get this slow, it's not something you can watch, it's not quick. You'd have to sit there for a long time, but it can cause that deeper infiltration into the deeper soil. All right, hang on just a sec here. All right, so the next topic on weird roots. Does that look familiar to you? Bugs Bunny, you all still know about that? I'm not totally dating myself. All right, so Bugs Bunny, be very, very quiet. We're hunting. So the quotes I'm gonna put here are actually taken from an interview, NPR, when I was washing dishes one Saturday morning listening, and they were interviewing this father-son team that have their own business. And they hunt, but not what you think. So this is a quote. Out in the boggy Virginia forest, the hunter quietly stalks. He circles a particular tree a few times, then picks his spot and lifts his 20-gauge shotgun. Blam! His prey falls to the ground in an inglorious whir. Another sprig of mistletoe bites the dust. I had no idea that this is how they actually harvest mistletoe. They actually shoot it out of trees. And it's like an art form. So I'm washing dishes and I'm like half listening and I'm like, what? But I had never really given it any thought. Like, how do they go? And I mean, I knew where mistletoe lived up in branches. I'm like, but I didn't really think about it. But there's a lot of mistletoe sold during the holidays. It's a business. And so I just was laughing. I stopped washing dishes and just listened because the father-son team were just hilarious to listen to, of how they were so excited to describe this to somebody who actually wanted to learn about it. So those cute little wonders of nature, those totems of romanticism that turn Scrooges into smoochers during the holiday season often find their way to doorways by first getting themselves blasted out of treetops. Blowing it out of the sky is the West Virginia way, said Charlie Spencer, a state forestry specialist who's hunted mistletoe for years. And a shotgun is just the most effective way to get it out. So apparently where it tends to grow in the southern states, it's not like they have logging roads into those areas. You can't drag a ladder or a big piece of equipment with like what they do on the, what's that called? The big arm that gets you way up high.
Cherry picker.
Yes, cherry picker, something like that. You just can't do that in the forest system. So they actually hunt it out, and they said it's really an art form because you have to know where to shoot it to not damage the tree and not blow the mistletoe into too small of pieces, because then it's not marketable. You need big pieces. And so he said it's a real art form to be able to aim and shoot it out and be able to get stuff that you can actually sell. And so this is a parasitic root that we're thinking about now. And it is a very interesting plant with a lot of folklore. It forms these really nice fruits that are very, very sticky. And we don't really eat them, but a special bird does called the mistletoe bird. And it likes to eat the berries as it's sitting on a branch right there. It'll just keep picking the berries and eating it. And then about like half hour later, it starts pooping out the berries, and they're super sticky. And so it'll stick to the end of his butt. And there's video. Sir David Attenborough, I think, captured some really good video. If I can find an active link, I'll post it. But they show the bird like trying to get rid of the sticky thing on its butt. And so it starts to move across the branch and kind of wipe its butt on the branch. And then the fruit gets stuck to the branch. The root comes out, the seed germinates, the root comes out, plugs right into the branch. So it's an ingenious adaptation. I mean, it's all through natural selection and adaptation that you have this interesting coevolution between this particular bird and this very sticky berry. And that's because that's another thing. It's like, how the heck does it get up there? And it's through this, they really don't leave. The mistletoe bird just sits there.
Where do they go?
Yeah, I guess the mistletoe bird, it's very eye-catching to them visually. It still pops with the green background. It's enough to catch their eye. But yeah, I started looking more into it after I heard that interview. And what really gets me miffed with this plant is it's a hemiparasite, they call it, which means it can do photosynthesis if it really wants to. It just chooses to parasitize. So it's kind of a lazy plant. It's like, yeah, I people can do it, but I'd rather just parasitize. So it's a hemiparasite. And it's kind of odd that they pick a parasitic plant to be this romantic thing. So technically it's an epiphyte, which means it lives on other plants. Now, not all epiphytes are parasitic. Most epiphytes are totally cool with their host plant they're sitting on. And they don't bother that plant, but mistletoe does. And so the root comes right out of that berry that's stuck to the branch and will start to plug into the xylem and phloem and get access to the nutrients from the plant. We don't have it up here. It's mostly in the southern eastern states, but it does really have a lot of folklore. I love the little bit of time I spent online. Lots of folklore and medicinal uses. And there's an old saying that if you meet under the mistletoe, if you had warring enemies, they had to put down and like call a ceasefire until the next day. So it had a lot of power in regard to how kind of universally people had a lot of revere for this plant. So this is a close-up of a tree that is in the wintertime, so most of its leaves are down, but you see the mistletoe stays nice and green. And that was another thing that was very eye-catching to humans, is that it was like the only thing around in the wintertime that was, you know, vibrant and living and showing, you know, some vibrancy. And so that was also what led to some of the folklore about increasing fertility and things like that. And the Celtic Druids, the Norsemen, they held it sacred because it was something that persisted through the winter. Whoops. And even as just in the early, the Great Depression in the early 1900s, that was also, you know, a sign of resiliency. It was a very tough time for people around the world. And so that green, vibrant mistletoe. And so I guess, you know, you can understand why they would tend to revere it, but it's not a nice plant all in all. So it's kind of interesting that it, but you know, they weren't plant biologists. They didn't know, you know, now we know it's a hemiparasite, but you know, you can see why, especially when they get really well infested like that in the wintertime, that would really catch your eye. So I have down in the notes this YouTube link. That's the mistletoe bird. So I think that link works, but if not, I'll try to find another one. But I saw this saying too, mistletoe. Mistletoe grows on trees and feeds on them like a parasite to survive. So why do we kiss under parasites in December? Yeah, I like that viewpoint. Kind of interesting. So even Tigger gets into it. Good old Tigger. Yeah.
It's typically found as red, but they're white because people mix it up with holly.
Oh, yeah, holly's red. As far as I know, it's white. I don't know that I've ever seen, it might be the holly berries that people are say are mistletoe. Yeah, holly is very common. Yeah, holly is a very common Christmas decoration with red berries. But mistletoe, it's usually just little sprigs that you hang from a ceiling. So there are some red ones. There are some cultivars.
Okay, so you.
Okay. Oh, I've only seen the white. Even fake. If I buy fake mistletoe, you know, it's white. So, yeah. So anyways, something fun. As I know it's not mistletoe season, but we just got done with Valentine's Day. So I'll post that in case you want to share that with any non-botany friends and educate them. I'll put it.
How jays are, and we're talking about European jays, and I was talking about the American.
Well, yeah. So
It was really heated for the.
yeah.
About different birds.
Yeah, clarification on, well, what exactly, which type? All right, let's go back. So mistletoe, again, you know, it's just kind of a lazy plant. It can do photosynthesis. It just chooses not to. But this is found, you know, around the world. I think this picture is actually taken from Australia. They have a fair bit of it in Australia as well. Here's another parasitic plant, believe it or not. Doesn't that kind of look like a fungus? That's the first thing I used to think of too. But that's actually anyway, if you've ever touched it, it's very much the texture of a fungus, but it's not. It is a parasitic plant. This is Monotropa genus, and it is, you know, that whitish color because there's no chlorophyll. So this truly is a parasite. It cannot do photosynthesis on its own. And if you stumble on a patch of this in this area, you're lucky. It's very challenging to find. At least I don't run across it. Super common.
I know where there's a ton of it.
Where?
Maybe the alcohol recreation area.
Alqual,
There's not-
is there?
Yes,
You go on the Forestville bike trail, the biking trail.
Yes, I've seen
Yeah,
it
they're
there,
everywhere.
but it's not every year. So like I'll go to the same patch and it's not there that year,
Fair.
you know?
Yeah.
I've seen some.
yes.
Yes, I found it there too. But I went there and then there's another one right on the, that little patch of woods by the medical center, right by McClellan. There's a nice patch in that little, there's a nice patch of that in that patch of woods, but the next year I went to it, it was all gone. It just didn't go, grow up that year, so. But this is interesting because it is totally parasitic on plants around it, and it's usually through a mycorrhizal fungus that it's getting fed. And so a fungus links this Monotropa to a nearby plant, and so the fungus serves as a bridge of transferring the nutrients.
Do things eat it?
Yeah, I don't know. I have seen like slugs on it. So I'm guessing certain insects. Yeah,
Is it not starchy enough?
I don't know. Yeah, I don't know, because I mean, normally, I don't know. I know one of the medicinal plant chem students, Ben, I don't know if anyone knew Ben Brickle, but he's been gone now a couple years. He graduated. He did a special project. I think his capstone project was on Monotropa. And I think he worked with Dr. Wilson, and they were looking at some of the chemical profile of it. But other than that, I don't really know much about it. I just know I feel really lucky when I find it that summer, you know, it's not common. But yeah, truly, it'll never really green up. It doesn't have the chlorophyll pigment, you know, it's just like totally dependent. And then a graduate student, not here, but a graduate student was the one who figured out that this plant hooks to a mycorrhizal fungus that then hooks into another plant. That was his master's thesis. And so that was a really nice find for him. This is another one that you might see in an agricultural field. And it's very pretty. These lovely red flowers, very dainty. It looks really cute, but this is a nasty bugger. So this is Striga. And it is actually, there's a plant hormone called strigalactone named after Striga, this parasitic plant, because it, they discovered the hormone in that plant initially, but then they realized a lot of plants have that hormone. But anyways, what you're seeing here is the plant is growing at the base of a corn plant, and it is tapping into its roots into the corn and parasitizing. And so here on the right, this is the corn, so I'll label it C. That's the corn stem and root area. And then here is the root system of the Striga, and they call this area that's plugging in, they call it a hostoria. That's kind of a generic term that we use for things that plug in, kind of invade other tissue and can be parasitic or not. That's just kind of a general term. But anyways, that's what's going on. It's able to plug into the corn plant and get the nutrients from the corn. The problem is that it's a very prolific seed producer. And so it drops its seeds. It produces there's a nice seed bank in the soil of this parasite, so it can be every spring, it starts to sprout up and it can take a while for it to get established, so the grower doesn't notice it at first, and then the corn plants are there and that kind of obscures it. You really have to kind of walk the field or have a robot go through to ID that it's there. It's a real problem. They're trying to figure out ways to solve this from several different avenues. No, that's its most famous kind of like where it was initially discovered and well studied. I don't think it's limited just to corn, but that it seems like more often than not, corn is the one that's at risk with this parasite. So it is bad because then your corn plant doesn't get enough of its needs met. And so the biomass yield at the end of harvest season can be quite challenging for the grower. They're trying to put resistance genes into the corn. That has not been successful as far as I know to date. They're trying to do herbicide resistance. They're trying to find an herbicide that can kill Striga but keep the crop plant unharmed. And so they're trying to do some genetic modification. As far as I know, that hasn't been totally successful either. This one has some success where before they plant the corn, they go through and spray the field with a hormone to get the seeds to germinate, and probably gibberellin of some kind, and the Striga, get the Striga seeds to germinate, and then they can spray with an herbicide. So, and then after that, they'll go ahead and plant their corn. So basically they're trying many different things to get rid of it. It's that big of a problem. And so unfortunately, like I said, it's kind of hard to identify because it stays so low to the ground. You don't always see it until it's established. So
Some might cause significant crop loss then.
yeah, I mean, the corn plant will still grow. It just doesn't create as much corn on the cob. It's probably not as sweet, you know, that can mess with your livelihood really quickly. So parasitic roots can be a really, really bad thing. And then just root systems in general. This is a picture of my brother-in-law. He was on his brother's property, and after a big windstorm came through here in the Marquette area, and I asked if I could post that picture because that's impressive. That's a tree that's overturned. You can see how big the tree trunk is, quite big. Pretty massive.
Herbicide resistance to Striga, and says as of May last year.
They finally got one. Yay. Not that I love herbicides, but you know, it's a problem. Yeah, yay and boo. It's a yay boo thing. So yeah. But this I put here just to kind of visually hit you with the idea that for many plants that you see, the biomass below ground is bigger than what you see above ground. It's not 100%, but in many, many cases, the biomass below ground is much bigger than what you see above ground. So keep that in mind as you're walking and hiking around. The root systems can get quite extensive. And then in forest systems like this, you can have root systems grafting together with other nearby root systems. And so it can be this kind of continuous thing. And then you add in the mycorrhizal fungi that are also down there connecting these different root systems, which we'll talk about when we get into the beautiful fungi in a couple of weeks. So, but impressive root systems for sure. Okay, any other questions on roots? So they get short shrift a lot because we don't see them visually, so we tend to not think too much about them, but please spend time studying the wonderful roots. It's a very dynamic part of the plant body and so different than, you know, the above ground, what the above ground portion has to deal with. And so very interesting to think about. So now we're going into stems. I believe that's posted and available for you in EduCat. And okay, so now we have to think about stem tissue. We're going to zoom in mostly on angiosperms, the flowering plants. And again, remember, once you start thinking about angiosperms, the first thing you think about is this going to be a dicot plant or a monocot plant? Those are your two options initially. And so here you're looking at those two options, and you can see visually very different in terms of how they arrange their vascular tissue with respect to the rest of the stem tissue. And that's really what you're focusing on as you try to identify, what am I looking at? One of the big things that can tell you that is, how is the vascular tissue arranged? So let's look at, believe it or not, this is a dicot stem. So, which seems weird, because when we looked at roots, it was the opposite. And so when I was first learning this thing, I'm like, wait, what? Because I told you last week, a monocot root has a single ring of vascular tissue. Now I'm telling you a dicot stem has a single ring of vascular tissue. So that's a little confusing, and I'm gonna hopefully dispel the confusion here, but let's first think about this. So let's pick this apart. Let's start from the outside in. So if it's this is a young stem. It has, I don't know exactly what plant this is. It has not formed any bark yet. All right, if it is going to, I don't know. So the very outside is still just the epidermis. You don't have any bark yet. And then you have the cortex region, which is just pretty much the rest of it. And then you have the ring of vascular tissue. So you have, like, you can tell there's like discrete bunches of vascular tissue, but in general, taken as a whole, you see it's a ring of vascular tissue. So here you can see, if we go up here, the reddish, purpley, to my eye, it kind of looks reddish purple, the big cells there, big in diameter, that's the xylem, right? And then the very petite looking, kind of bluish green, those are phloem. And then you have fiber, like a little hatch of fiber bundles kept. And then all this middle part, that's just all a bunch of parenchyma cells that are filling in there. Whoops, where did that go? So the other thing to look at here, which is hard to see on this, so if we ever ask you to identify the vascular cambium, we'll give you a clear shot. But basically, what you're zooming into is in between the xylem and the phloem in this ring is the vascular cambium. Whoops. And it's hard for me even to draw it correctly. So if you can see the red line there, that is approximately where the vascular cambium is. So the vascular cambium is a ring of cells, meristematic cells, right? And so they're sandwiched in between the xylem and the phloem, single ring, and they're actively dividing. So if this is a stem of an oak tree, this is a baby oak, it's, as you know, there's some oak trees that are very big in diameter, their stem tissue, very big. That's the vascular cambium doing its job. It's giving girth, diameter growth to stems. And so when these cells, that vascular cambium, when they go through cell division, it's really interesting, because usually when one cell goes through cell division, you're left with two progeny cells that are, pretty much the same. You don't get that. Here, the vascular cambium says, okay, I'm going through cell division, and I'm going to produce a xylem cell to the inside and a phloem cell to the outside. And every year they'll do that again, xylem to the inside, phloem to the outside. And that way you keep getting this bigger and bigger diameter to the stem tissue. So pretty interesting meristematic tissue there. So the fancy term is secondary growth. So if you see that, that just means you have that meristematic tissue giving growth in a diameter, increasing the diameter. Sometimes they'll call this inner portion the pith. I don't really use that term. I don't really care that you know that term, but you'll hear it.
Is that what causes like tree rings to form?
Yes, absolutely. And we'll look at that. We're gonna look at that. And so, okay, let's go, okay, so hold this thought with the dicot and let's compare with the monocot. So with monocot stems, you can see a very different design. Yes,
Exactly, is just like parent.
it's just parenchyma. Yeah, yeah, you got it. It's just a region. So when they say the pith, they mean that central region. Why can't they just say central region? I don't know. But, you know,
Things like, isn't that what like the nasty like white stuff on the orange and the peel it's called?
oh yeah, yeah, the bitter stuff you bite
It's
into.
like in the middle.
Yeah, 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 that's true. So going from the outside in again, you have an epidermis. And you have just a scattering of vascular bundles. So by this design, it does not allow for a ring of vascular cambium cells. There isn't vascular cambium here. There isn't any of that. And then they just say the rest of it's all just a cortex region. Again, most of it's parenchyma. But you see this scattering of vascular tissue through the whole stem. There's no vascular cambium anywhere. That means monocots really don't get significantly big in girth or diameter. Their stem tissue just doesn't do that. They're very limited on how wide they can get with their stem tissue. So that's a huge difference when you think about the stem comparison between the monocot versus the dicot. Okay. Can't remember if I don't, this might be your first look at this one. I can't remember. Very often when they discover a plant and they don't know what it is, what they do is they start looking at vascular tissue arrangement. That's one of the things that they zoom in on because we know that certain designs belong to certain types of plants, monocot versus dicot, ancient versus more modern. And so when they examine the fossil record too, they're looking at this kind of thing if it's available to see. So here up top, A and B, we'll come back to this image because these are some of the arrangements of vascular bundles in the seedless vascular plants, which are more primitive than angiosperms. So we're going to come back to those when we cover that group of plants. But here you can see, if you look down here, they're getting into some options for vascular tissue arrangement. So here they're talking about some dicots do this, some gymnosperms. So again, it's a little bit more ancient. Gymnosperms are more ancient than the angiosperm. Again, some gymnosperms have this arrangement. And then here you're looking at the monocots. So these are what you see under the microscope, and then the drawings are right above it. And so they're trying to show, I guess they're using xylem, the blue, I guess, for water or water transport, and then the green for sugar transport, I guess, is how they're color coding that. So we'll come back to this, but it is something that we look at when we're trying to identify what what kind of plant is this? And so I had a really hard time when I was taking my first botany class because this image here in the lower left is a snippet of a dicot root. Remember I said it has that plus configuration with the xylem. And it's nice and red, you have that plus sign and the phloem is in each of the corners. And so now I just told you, but a dicot stem is a ring. And I could not for the life of me figure out how that worked until I saw this picture. And then it's like, oh, so what happens is you have your dicot root with a plus configuration, and then you have a transition zone at the start of the stem, right at the base, right where it's into the soil. And you can see this transition zone as, you know, this gradual shift in morphology until you do end up with a ring of cells, ring of vascular tissue in the stem tissue. So if that helps you visually imagine, because you will need to know the difference, like, and on the next exam in lecture, I probably will have some visuals on, is this a dicot stem? Is it a root? What are we looking at here? So I will spend some time working with you on that. So here, under the microscope, that's your dicot stem. Now, someone might look at that and go, well, how do you know it's not a monocot root? And the trick is, think like an architect. If you're going to build a high rise, you know, a skyscraper in downtown Chicago, you don't put the heavy steel beams right in the middle. You create this framework that will be the perimeter of the building with the really, you know, strong steel. And then you build your skyscraper on that framework. So the fact that the vascular tissue is so close to the perimeter, it's really close. It's not in the center here. That's your dead giveaway, that you're looking at stem tissue, because stems need that kind of strong tissue. And remember, xylem in particular, it's dead cells, very strong. Fibers, dead cells, very strong. So if you have those around near the perimeter of the stem, that will keep your stem nicely upright, provide really good structural support. Even getting knocked into, heavy windstorm, they should be okay. So monocot stems, they don't have any vascular cambium. So now we're typically thinking about plants that don't form significant girth to their stem. They don't do bark either. They don't do bark. So we're thinking about herbaceous plants, the ones that don't have true bark tissue. They don't get big in diameter. And so if you zoom in to one of the bundles of vascular tissue, they often refer to it as the monkey face design, a surprised monkey. And so you have the eyes, nose, and mouth as the vessels of, you know, so that's xylem. You've got your big vessel with the V as the big vessel. The tracheids are the cheek and chin typically of the monkey face. And then the forehead tends to be where you'll find the phloem tissue. And then you typically have a ring of cells around that called the bundle sheath, like we've been talking about. They're just not in this design anyways. They're not ramped up in this particular picture. So scattered, here's an actual monocot under the microscope. It's not quite as pretty as the drawing, but if you look carefully, you would see the xylem and phloem, but this one's not so good. This one's better. This is actually bamboo with hollow center, but you can see the vascular tissue. Bamboo, because it tends to grow in pretty wet environments, it doesn't have a ton of xylem. It does have some. Okay, so let's go back to the dicot. So here is an older dicot compared to what I've shown you so far. In the sense that it has tree rings now, and you're seeing that in the purple. So this is nicely drawn out where the vascular cambium is the red ring, and then you can see the phloem is represented by the green, and you see lots of xylem. The xylem is the purple. So the way the artist drew this, it might seem weird because I just finished telling you when the cambium cells divide, they produce one xylem to the inside, one phloem to the out. So if you follow that out over several years, what I just told you, you would think that there'd be a lot more phloem here, like it'd be even Steven, right? What you see for phloem, you're going to see that, or xylem, you're going to see that for phloem in terms of amount. But it doesn't work out that way. What tends to happen is the older phloem starts to actually break due to pressure forces. And so you really do end up with a rather skinny area of phloem that's active and alive and doing what it needs to do. But you get a buildup of xylem because remember xylem, those are dead cells anyways, and they're very tough. Got all that lignin, so they don't break down. They stay there. But the phloem is more fragile. It doesn't have a secondary cell wall. And so over time, the older phloem will break. So that's why you don't see this even Steven growth of phloem and xylem over the years. How many years do you think, if you look at the rings of xylem, how many years do you think this might be? I count 4. The yellow I don't count. So this looks like a 4-year-old seedling or young sapling. The ray tissue is it's an avenue for getting nutrients across the diameter of the tissue. That's why they do that. Okay, so in words, what we just looked at was that red ring of vascular cambium. And this idea that you're going to get cell division to occur in the cambium on a fairly regular basis, hopefully in the summertime, where xylem gets produced to the inside and phloem to the outside. And so the xylem starts to build up and becomes the tree rings that you can count. People will refer to the xylem as wood. So the foresters and people, they'll talk about the wood, but technically it's just all secondary xylem that you're looking at in the stem, and they give rise to growth rings over the seasons. So what tends to happen, especially if you have a really big diameter tree, you'll get the newest xylem will be very active for water transport and mineral transport, but the stuff closer to the center of the tree tends to stop working for water flow. Sometimes it fills up with resins and tannins and things like that, and isn't working as water conduction, but it is still valuable to the tree and to the plant. So the secondary phloem, we're going to learn a little bit later in the slide set, the definition of bark. And the way they define it, the phloem tissue is part of the bark tissue, which seems a little weird, but that's how they do it. And so, like I said, the older phloem breaks because it's not as tough as the xylem in design. And so you get a much thinner band of active phloem. But you can definitely use the secondary xylem, count up the rings on that to see how old. So here's another image. How many years do you think this one is? Yeah, 3. It looks like 3. I don't count the middle. So this one, you can kind of see a nice delineation in design. And so right in the middle of that, that's your vascular cambium. So it looks like it's kind of a bluish color here where the vascular cambium is. So if you follow that all the way around, so when it's dividing, it's giving you that xylem to the inside and the phloem to the outside. And so here, interesting too. So this was probably taken at the end of the growing season, probably in fall, would be my guess. The reason I'm saying that is that, so this year's growth, is this growth rate. And you can see how they're a little bit more consistently big in this region and not so big closer to the vascular cambium. Can you kind of see that pattern? So the fact that they're bigger in this region here, what kind of xylem is that? So they're bigger in diameter. The vessels. So plants, angiosperms are really quite savvy. In the spring, This was probably a good spring where it was nice and wet. The soil was nice and moist. So in the spring, angiosperms tend to lay down a lot of vessels because they have plenty of water. Vessels are more efficient for water uptake. So they put down these nice efficient vessels and get a lot of good water and mineral uptake through the spring. And then as the drier summer comes around, sometimes it's drought prone, then they start laying down the trichids that are a little bit smaller, not quite as efficient. However, it gives them one big advantage because if they always just did vessels, when drought hits, it tends to create the tree version of an embolism in the vascular tissue. Are embolisms good for humans? No, you can die. All right, so I'll explain a little bit more about that as we get further into this, but basically, when you get into a drought, it's really smart. If you're a smart tree, you'll say, okay, I'll switch to trichids now. And that will stop embolisms, hopefully, from occurring and causing that vascular tissue in that region to stop working. It doesn't kill the plant like it kills a human, an embolism, but it does create a situation where water will stop flowing. That's why they always create lots of trichids and vessels right near each other, and then they can reroute the water if they have to. So I'll describe a little bit more about that, but it's a really interesting switch that they'll do and it's all in response to how much water do I have, and they'll switch what kind of cells they end up laying down. Here's another image where you can see the xylem stained red, and vascular cambium is the delineation between the red and the blue, where the blue is the phloem. Okay. Yes.
So, just to clarify, the, vascular cambium area there, that would be visually the growth ring.
So this would be like a growth ring. Here.
Well, like, because we see like the line where it's edge. Is that the vascular cambium or is
Yeah,
that?
right here is the vascular cambium. Right. So the vascular cambium is producing the xylem to the inside and the phloem to the outside. Other questions? Okay, let's stop there. We'll get more into stems Wednesday and probably get into leaf tissue as well.